What if one tunnel machine could mechanically excavate rock and adapt when conventional boring is no longer enough?
The problem begins when geological conditions suddenly change. A cutter-head designed for fractured rock can slow dramatically when it encounters much harder formations. When the rock becomes exceptionally hard, mechanical excavation can slow down dramatically, increasing cutting tool wear and excavation time. The harder the rock becomes, the greater the cutting forces and tool wear, making purely mechanical excavation slower and more demanding. When the rock becomes too resistant for efficient mechanical cutting, controlled drill and blast excavation can fracture the rock ahead of the machine. Once the rock is fractured, the excavated material must be removed continuously. Efficient muck handling is essential to keeping the tunnel advance moving.
Instead of relying on one excavation method, engineers can adapt the strategy to the geology encountered ahead.
The advantage is flexibility. Mechanical cutting can handle workable rock, while controlled fracturing can help overcome tougher zones. The real advantage is adaptability. The excavation process can respond to changing geology while keeping the tunnel advance moving. The objective is continuous advance. Excavate the rock, remove the muck, stabilize the opening, and prepare the face for the next excavation cycle. Excavation is only half the job. Engineers must immediately stabilize the surrounding rock mass using systems such as rock bolts and fiber-reinforced shotcrete. After the ground is stabilized, a permanent reinforced concrete lining provides long-term structural support, durability, and a controlled tunnel profile.
Groundwater is another challenge. Waterproof membranes and drainage systems control infiltration, protecting the lining and keeping the tunnel serviceable for decades.
Behind the lining, groundwater can create hydrostatic pressure. Controlled drainage helps relieve that pressure and protects the tunnel structure over the long term. Even after construction, sensors and inspections monitor deformation, strain, and vibration, helping engineers detect problems before they become serious.
The key advantage is flexibility. Instead of forcing one excavation method through every geological condition, engineers can adapt the excavation strategy to the rock ahead.
Technology like this could be valuable wherever long tunnels encounter complex geology, from mountain railways and highways to major underground infrastructure projects.
But no machine eliminates the challenges of tunneling. Geology, tool wear, ground stability, ventilation, and safety still demand constant engineering control.
The future of tunneling may be even more adaptive, using real-time geological data and intelligent monitoring to help engineers optimize excavation as conditions change.
After years of engineering, excavation, and construction, the result is a tunnel capable of carrying high-speed transportation safely through the mountain. From hard rock excavation to ground support, drainage, and permanent lining, adaptive tunneling technology could reshape how engineers tackle some of the world's most difficult underground projects.